Does anyone have any homework questions? And we were still in 3.2. And we're looking at various limits, computing the definition of the derivative. So the last few examples, we've been finding the derivative function according to the definition of the derivative. Does anyone have any questions on any of those? Okay. There's a couple more things in 3.2 that we're going to look at. I guess, yeah, they're kind of related, but we're going to look at how to, like, if we're given a function, how do we graph the derivative? But let's go ahead. There's a couple of versions of the derivative notation. So when it says find the derivative, we have derivative notation. One of them we've been using frequently, which is f prime. That means find the derivative. Another one is dy over dx. So that's also acceptable notation for f prime. And when we write dy dx, it does give us an indication of what the derivative is. This d we're just going to think of as a tiny change in the y over a tiny change in the x. So, you know, looking at it like that, dy over dx, we do see that it is a slope. But the tiny change with respect to x and y give us the slope at a point, basically. You know, compare that to like the regular slope formula or the average rate of change formula, where you just had some change in y over some change in x. You know, this change is generally large in comparison to the dy and the dx. Sometimes we'll write d over dx. So in all of these notations, you know, it's telling us take the derivative with respect to the variable x, and that's kind of what this is saying. It's this notation here in number 2. It's kind of, we kind of read it as, or interpret it as, the derivative of function y, or whatever's on top, the derivative of y with respect to the variable x. So that independent variable on the bottom, the function's name is on top. You know, like if you had a position function, and they called it s of t, position at some time, I don't know, it's t squared minus 4 or whatever. Like we could say take the derivative of that function s with respect to the variable t. So that's also the same thing as saying find s prime of t, or the derivative of s, function s with respect to t. That avoids being a little odd. So just a couple of different ways to notate the derivative. Yeah, and so here in number 3, there's typically a function of x sitting here. So we'll put that here. You know, typically in physics classes, they'll use the second notation when you find derivatives. But anyways, those are some common notations for the derivative, just so you're aware. Does anyone have any questions on that? So the next thing we're going to look at is graphing the derivative. So when we're given a function and we're asked to graph the derivative, we're thinking of the derivative as the slope of that function at all points. So we're really going to look for these four things here. And we're going to look for when the slope is positive, when the slope is negative, when the slope is horizontal, and when the slope is undefined. So anytime we graph a derivative, so like if this is f prime, it's still going to share the same x values. But the outputs when we graph the derivative are simply the slopes. Are the slopes, you know, is if I put my pencil down on that curve, is the slope positive or is it the slope negative? If we have positive slopes, then, you know, our points are going up here where things are positive. If the slopes are negative, then the point at each x value is going to be down here. When the slope of the tangent line is horizontal or flat, then we have a zero slope, so those are directly on the axis. And when it's undefined, either you're going to have a hole in the graph of the derivative or you're going to have a vertical asymptote in the graph of the derivative. Okay. So hopefully at least the first three make a little bit of sense. The fourth one, we really haven't discussed the instances where the derivative is undefined. So for that one, we have the A, B, and C below. So that's for when the derivative is undefined, or for these three parts. And those are all illustrated here in these graphs as well. So when a function is not differentiable at a point, what does differentiable mean again? What does it mean to be differentiable at a point?
It means that the derivative itself exists.
Right. It means the derivative is defined or the derivative exists at that point. So when we say something's not differentiable at a point, what we mean is like on that graph you cannot find the derivative at that point. The three instances are if f isn't continuous at a point, but f has a corner or a vertical tangent. So, you know, here in part A, the function's not continuous. You cannot define a derivative at A. Because remember, the derivative is defined in terms of the limit as h approaches 0 on the slopes of the secant lines. So that's a two-sided limit. You know, when we set this up and we said, all right, well, let's look at that alternative notation. Here's our function. Here's x value. Here's an x plus h value. You know, this is kind of the situation we were in. Let h approach 0 and this point approaches this point. But we're really doing that from both sides simultaneously. This here could also be considered x plus h. But in that instance, if we're to the left of x, then h is just a negative value, right? So you've got to be able to approach, you know, if we're trying to find the derivative at this point here, there's no way we can approach from the right, because there's no function over there, right? It's not doing something like that. Same thing for this point here. The function's not even defined there, so there's no way you can find a derivative there. It's almost akin to saying, remember when we thought about continuity, for the most part, we had functions that were continuous on their domains. If we took like the square root function and said, find the derivative of the square root function over here at -2, it simply doesn't exist. The function's not defined there. So the notion of being differentiable, the derivative exists, and continuity is specified in a few more pages. But that's the idea. When the function's not continuous, you can't take a derivative or find a derivative there. For part B, when it has a corner, I don't know how clear that is if y'all printed that out. But when a function has a corner, the reason we're not being able to define a derivative there is based on the same argument. We can approach a corner from both directions simultaneously. But those limits have to be equal. And in the sense of the derivative, the limit was outputting the slope of the line, right? The slope of the tangent line. So if we look at approaching, if we're talking about this point and h approaches 0 from this direction, then we have this particular slope, whatever that is, we'll call it m. But if we approach from the other direction, we have this particular slope, which is negative m. And since if we look at from the left and the right, you have two different slopes at that single point, more or less. It doesn't make sense to say, you know, one or the other is the slope of the tangent line there, because it has to just be a single thing. Okay. So derivatives aren't defined at sharp corners. Let's see if this works. The absolute value is a good example of that. You have basically two different derivatives there. And then the third and final was when we have a vertical tangent. So that's like the graph of over here in part 320 part B. That's like the graph of maybe like x to the 1/3 or something, where as we get closer and closer to 0, the slope of that curve gets more and more vertical. So it's kind of vertical right here, right? So you've got an infinite slope. The tangent line is infinite. So that's a vertical tangent line. So if on whatever that function is, if this is the cube root of x, I believe, and it said find the derivative at 0, you can't do that. Just like if I wrote this function down and said, hey, this function, whatever it is, has a derivative of 1 over x squared, find the derivative when x is equal to 0. You can't do that. You can't plug 0 into your derivative. So those are the things we're going to look at when we're graphing the derivative. So it'll say, here's the function. What does the derivative look like based off of this function? So that's kind of all the nuts and bolts there. Let's look at some examples to make sense out of that. So we have the following function f of x given above. What we want to do is graph the derivative here. So our y values, the outputs on this graph, are simply the slopes of the curves at various parts throughout. The x values here are the same x values here. So we're going to look at this piece here. First of all, this piece. And, you know, you just, like if this is all, these are like line segments, but if you've got a curve, you know, just imagining your pencil floating along the curve, whatever it's doing, and at each point you're saying, what's the slope? Is the slope positive? Yeah, it's positive. Positive, still positive, but it's getting less positive. Now it's 0, now it's negative. Those are the outputs that we're plugging in, or plotting on the derivative. So for a linear segment like this, we don't really have to think about it because the slopes are always the same. Whether I'm at this point here, this point here, or this point here, or this point here, the slope is always the same, right? The derivative is always the same on that line segment. So based on that line segment, what would the slope of the derivative be? Yeah, it's just -1, right? We go from one point to the next. I go left 1 and up 1. So since the slope on that segment, let's label this x value from we're looking at -5 all the way to -2. So since that slope is always -1, the output of the derivative will always be -1. Because no matter what x value we're at, the slope is always -1, and the derivative is always -1. So then what that's going to look like is just a straight line. It's constant. The slope is always -1. Does that make sense? Anyone have any questions about that? Yeah. Say that again? This right here? I don't, yeah, it's at -1. Because the slope of that green line is -1. But then we also have to ask ourselves, well, as we get up to an x value of -2, can we define the derivative right here?
Yes.
No. The derivative isn't defined at sharp corners. So we have to indicate that. Like we indicate any something that's undefined. Clearly that the tangent line there or the slopes aren't getting more and more vertical, right? If they were getting more and more vertical, we would have an asymptote here instead of a hole. But there is an actual point as we go from the left. It's still negative, the slope is still -1, but it's sort of like when we bend around that point is where it's undefined. So we have to indicate as soon as we get up to -2, things are changing drastically for that second piece. So the second piece, it's still linear, so no matter what point we're looking at, putting our pencil or whatever, that's always a slope of what? Yeah, up 1 over 1, slope is 1. So +1 is the slope, is the derivative, that's the output, that is always outputting +1. And the x values we're looking for, are from -2 to an x value of 0. So we're just going to draw this line from -2 to 0. Again, if this line on the right, is it defined, or the slopes rather, are they defined at -2? Are they defined at 0? No, so we're going to just indicate that here and here. But in between, it's always 1. The output of the derivative is always 1. Any questions? And our third line segment from 0 to +5. Do this out here. What's the slope of that line? -1/2, do you all agree? -1/2. So the derivative at every point except for at the ends will always output -1/2. So we're going to say, all right, from, let me move that over rather. From an x value of 0, which the derivative is not defined, all the way to an x value of 5. That's always outputting 1/2. And so it stops right there. We don't really know what happens outside of that, so we'll just stop our line there and not speculate as to whether or not there's a point or a circle there. So that is the graph of this function's derivative. Remember, the derivative also tells us the instantaneous rate of change at every point. So are there any questions on that? Okay. Those are really the most straightforward cases when you have linear pieces, because the slope's always the same. Graphs like this, at every point the slope is different. So we're not going to be able to be as precise because we don't have any y values to actually measure the slope, and it's sort of a lot. It takes a lot of effort to measure the slope at every point, even if you did have the y values. So we're just going to try to get a reasonable representation of the derivative for this thing. Same x values as the original function. And so when you see like these curvy things, really you should try to identify where would the slope be horizontal or flat. So again, we're just putting our pencil along this curve and following it from left to right, just asking ourselves as we do that, at each point, do I have a positive, a zero, or a negative slope? And then that's going to tell us where we're plotting the derivative. Okay, so we're going to look at three points first. This point, here, here, and here. Because at those 3 points, the tangent line is flat or horizontal. Just at these 3 points. So what that corresponds to, you got a flat tangent line, a horizontal tangent line just corresponds to an x-intercept or a zero on the graph of the derivative. So that's here at -3, this one's here at -1, and this one's here at +1. Let's try to line this up the best I can. So at -3, the derivative, the slope of the tangent line is 0. At -1, the slope of the tangent line is 0, and at +1, the slope of the tangent line is 0. Does that make sense? Do you have any questions? Okay. So now that we know where it's 0, we'll just look at each segment and determine what's happening to the slope of the tangent line. So let's look at this segment right here. From here to here, what are the tangent lines doing? They're what? Positive slope, right? So if I said find the tangent line at this point, the slope of the tangent line at this point, you would say like that's really positive right there. The tangent line at this point is still positive, but it's less positive than the other one. The tangent line at this point, still positive, but again, less positive, and so on and so forth until we reach this, the 0 here, right? So they start off being really positive, and then they approach 0 or get less positive. So we're just going to illustrate that. They're going to start off positive, means we're above the x-axis on the graph of the derivative, and they get less positive going to 0. So I don't know, maybe they start off with a slope of 100 or something to that effect, but then it's a slope of 90, then it's a slope of 80, right? So we're discretely, if we looked at it, we would have points that, or outputs that look like that for slopes at specific points. Does that make sense? Does anyone have any questions or comments about that? We know to the left, or to the right of that point rather, this segment, what's happening? Yeah, so just put your pencil down. What is that slope right there? Positive or negative? Negative. What about the slope right here? A little less negative. How about this slope? A little less, and then it flattens out again. So they start out at 0 for directly next to that point where the slope is 0, and then they start off negative, and they get a little less negative, and they approach 0. Again, they approach 0. So since after that point they start off negative, we need our graph of the derivative to be down here. Right? They get a little, and maybe that's hard to visualize since we have so much stuff on here. But it's like, it's a little bit negative, then it's a lot negative, then it's a little less negative, then it flattens out again. So we're kind of also using where the derivative is 0 to guide us. We know we have to get back to that point at 0 when x is -1 on the graph of the derivative. So they start out a little negative, get more negative, and then they get less negative, back to 0 again. So, you know, it's not perfect, but it's the best we can really do. And after -1, we have this piece right here. What are the slopes doing on this piece right here?
They're positive, but they're getting more positive and sort of flattening out.
Yeah, so like this point right here, positive slope. This point right here, it's a little bit more positive. A little less, a little less. Flattening back out to 0 again. So they, after the x value of -1, the slopes are a little bit positive, getting more positive, approaching 0 after that. So they're a little bit positive, getting more positive, and then approaching 0. So something to that effect. And then the last piece after x value of 1, what are these slopes doing? Like at this point, the slope is negative. At this point, it's more negative. At this point, it's even more negative. So they start off slightly negative, but get more negative. So after this point, they start out slightly negative, but get more negative. So just something like that. As far as the exam goes, like I'll just have a graph of like 4 functions, and then I'll have a graph of 4 derivatives, and basically you just have to match the graph to its derivative. It's kind of, it's similar on MyMathLab, because they'll say, hey, here's f of x, and you've got a choice A, B, C, or D. What's the graph of its derivative? So we're not actually graphing anything by hand. We are in our notes just to get a sense of how that works. But yeah, any questions on that? Okay, so our third graph, be like this. Now this function f of x has 2 vertical asymptotes. Would it make sense to say the derivative is defined there? Can we find the slope of a tangent line at a vertical asymptote? Not exactly on that x value, can we? We can say what are the slopes of this, of this curve as we get closer and closer to the asymptote. But the fact of the matter is that the original function is undefined here, so the derivative will also be undefined. So you can always you can always use that information. What kind of undefinedness will the derivative have there? It just depends on what the function's doing. So towards these asymptotes on f of x, what's happening to the slopes? Or what is the derivative doing? Right, it's getting more and more vertical because we're approaching a vertical asymptote on the function. We would expect that no matter where we're at, these tangent lines here, 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 and here are pretty much vertical. So it's not like it's in that linear example, it's not approaching a specific value where it's undefined at a whole. They're getting more and more vertical. So on the graph of the derivative, we would also have vertical asymptotes at those locations. We'll just do the same thing we did on that other graph. We'll start over here with this piece. So like at this point, what are our slopes? Or what's the slope of the curve at that point, or the slope of the curve at that point?
Very small.
Is what?
Very small negative.
It's a really small negative number, right? Because we see, we're following the horizontal asymptote out here, so like as we get further and further out towards the left, we would expect that those slopes to be flattening out, right? Approaching zero. But we can just put our pencil right here and say, well, what's the slope right there? It's pretty much flat. We know that it's not 100% flat because that curve is not flattened out, but it certainly appears that way. So those slopes right there are really, really small negative numbers, pretty much zero, right? And then what happens to the slopes?
It goes more and more negative.
They just become more and more negative. So we're going to say here, the slopes are pretty much flat. They're not exactly flat, so we wouldn't say that they're on the axis, right? They're a little small negative numbers. So they're right here, they're right here, they're right here. And then they get more and more negative. So we're just going to plot more larger negative numbers. So the graph of the derivative, the slopes of that curve are pretty much the same as that curve. So they start out really small negative, and then they get more and more negative as it approaches the asymptote. Anyone have any questions on that? Yeah.
Where do you begin your graph? Like, how do you know where you begin it? Does that make sense?
Like
Why
like
is that
here, this
below the
piece?
x-axis rather than above the x-axis?
Yeah, so we know that it's above the x-axis, or below the x-axis rather than above the x-axis. You know, again, you might not be able to tell right here because it looks pretty much flat. But when that's sort of ambiguous, then we have to just scoot over a little bit more and say, what are those slopes next to it doing? So like if we scoot over a little bit more here, that's the slope right there is negative. So, you know, think about it going the other way. This is vertical here. But what are they doing next to it? Well, that slope, that slope, that slope, they're all negative. So it has to be negative getting more negative. Because, yeah, you always read your graph left to right. So we wouldn't start at this asymptote and read to the left and say, well, it's vertical, and then they're negative approaching zero, right? We start on the far left, and then, does that help? Like, yeah. You just kind of, sometimes you have to look at the ones next to it. You know, what is my pencil's flat here, but then if I follow the curve, what is it doing? Is it becoming negative? Or if I follow the curve, is it becoming positive? This has to be positive, getting close to zero, and this has to be negative, getting close to zero. So when it's negative, since it's negative rather, we know to start below the axis.
Sounds like the graph
No, we wouldn't do that because we're not actually given the full graph. It just based on what we have, it appears to be virtually flat there or almost zero there. We wouldn't speculate. You know, they don't give us the fact that this graph continues that way, so we're not going to speculate like where the graph is cut off. What happens there? Does it keep going? Is there an actual point that it stops at? We're just going to kind of do the same thing that they've done for that graph. So yeah, here we're zero. This pretty much looks like zero, but once you get right here, then you can tell if I draw a tangent line right there, that's a negative slope. Okay. So now the piece in the middle, notice the piece in the middle, if we're tracing with our pencil, it eventually reaches that point there where it's flat. So we do have somewhere in here, whatever this, you know, this value here perhaps is where the tangent line is horizontal, or the slope is zero. So at that point, I don't know what it is, it's just right there. At that x value on the graph of our derivative, we're going to have an intercept. Because the tangent line is identical to zero there. Okay. Looking at that curve again, on the far left, what are these slopes doing? Like, what is the slope of the line right here? Huh? Really negative, right? Negative right there, negative right there, negative right there, but it has to flatten out to zero. So it starts off super negative, but then flattens out to 0, or approaches 0 here. So it starts off super negative, we're way down here, super negative values, you know, getting closer and closer to 0. Any questions on that? Okay. And what does it do after the horizontal tangent here? After our horizontal tangent right here, what happens to our slopes? It becomes positive, right? So this slope kind of right here, it's a positive slope, and then they keep getting more and more positive, right? Positive, a little more positive, a lot more positive. So after this point, they're a little bit positive, and they start to get more and more positive. So something to that effect.
Would we be able to find the y-intercept just from the other graph?
Like this point right here, you mean? Or the
Yeah,
y-intercept?
the y.
No, so like we couldn't determine the y-intercept here. Because the output isn't, you know, this y value here at this point is whatever this y value is there, is whatever the slope is there. So since we can't measure the slope right there, we can't say what the y value is. Maybe that slope is 5, maybe it's 10, you know what I mean? Like if we knew that slope, if we had like y values here, we could say, well, you know, from here to here, what is that slope? Well, that slope is 10, then we would know that this y value is 10. Yeah,
Okay, that's
because the
fine.
y values on the derivative are simply the slopes of each line at every point. What's the slope of that line? That's the output of the derivative, right?
So what I'm getting at is that like the slope determines what like side of the x-axis the derivative starts on, right?
Yeah.
Okay, cool.
Right. Yeah. So like if you've got if your slopes are positive, if your you know pen or pencil is positive, then the graph of the derivative will be above the x-axis. If the slopes are negative, it's going to be below the x-axis. These two things here, and then where it's 0, it's on the x-axis or x-intercepts. Yeah, exactly. Okay, and then from the right, or to the right of our asymptote at 1, what are these slopes doing? Like what's the slope of this line here? Is that positive or negative? Negative. Still negative. Still negative. Getting less negative. So they start out really negative and get less negative. So we're going to start out down here below the x-axis, really negative, getting less negative. So that's a, you know, I guess a reasonably accurate picture of the derivative. Anyone have any questions? All right, final one. Example 4. G of x. And we're graphing G prime here. Same x values. So again, the first, we didn't do it with that other one, but the first thing I would look for is where your tangent line, the slope of the tangent line would be horizontal. So where on G of x would the slopes be horizontal?
-2 and 2.
-2 and 2, do y'all agree? -2 here or here?
At the discount. Yeah,
The top one?
yeah.
The top one? Do y'all agree with that? Slope of the tangent line is horizontal there. And here as well.
Would the holes not matter?
Do what?
Do the holes not matter?
So do the holes matter? The functions, g of x is clearly not defined at that point. But as we get closer and closer to this, what, you know, like what is our pencil doing as we're looking at these slopes right here?
Getting to 0.
It's getting flatter, right? So even though that we can't define the derivative at that point exactly, we can say that, well, pretty much to the right of that point, it's virtually flat right there. Same thing with this one at an x value of 2 and negative 2. You know, like right here, if we were to measure this slope, or right here, measuring that slope, it's virtually 0. So how close can we get to that deleted point? As close as we want, right? So those are, you know, they are where the derivative is 0. However, is the derivative defined when x is negative 2 and when x is positive 2? No, because there's a hole. The function's not defined. You can't define a derivative at a place the function doesn't exist.
So on G prime, does that mean there's a vertical asymptote at that point?
So on g prime, would that mean there's a vertical asymptote here at negative 2?
It's going to be small.
Since it's not defined. Possibly, right? How else do we illustrate where a function's undefined? With a hole. So we've got to determine, all right, well, when we're graphing this derivative, what happens at an x value of negative 2 when we're looking at that green slope? Is it an asymptote? No, how do you know it's not an asymptote?
Because it doesn't approach infinity or.
Yeah, right. The slope isn't getting super vertical at that hole, is it? It's getting super flat at the hole. So this here at negative 2 on the graph of the derivative, at least for that piece that's curving down, if you will, we have virtually a 0 slope, but it's undefined. So we're going to have a hole, I guess, in the derivative there. What about at positive 2? When x is positive 2, it's the exact same thing. The slope is virtually 0, but it's still not defined there. What about this piece? How do we graph the derivative of that piece? Find the slope, right? What's the slope of that line? Positive, right? So the best we can do. It's positive 5, maybe it's positive 20, who knows? It's clearly positive though, right? Is it always the same on that line? Yeah, just like our other linear functions. The best we can do here is say, well, since that slope is positive and always the same, we just know that it's some positive constant from negative 4 to this 2 right here. So, you know, whatever, here's our positive constant. We go from here to here for this piece. What happens at this point on the graph of g of x? Is the derivative defined there? There's a point on the graph of g of x, but can we find a slope at that point? No, it has to be from both directions, right? The function's not defined at negative 2. We can't indicate that the derivative is defined at negative 2 for either piece, right? If we said the derivative's defined here because the function has a point here, that's not true. You have to be able to find the derivative on the function g of x at negative 2, and we can't do that. So the derivative doesn't have a point there just because the function has a point there. Now, if it were this thing meeting up with this thing, then we have a definite derivative here. Because whether I come from this direction or this direction, both of those slopes are the same. Does that make sense? It's kind of like when you have like a flat or a horizontal tangent line at this point. What we're really looking at are the slopes here, like that, and the slopes here, like that. And the black line and the green line match up, therefore the derivative is defined there. We don't have that with these individual pieces. Okay. Let's do What are the slopes doing here to here? From -2 to x value of 0. They're negative, right? So it's pretty much 0 right there, but how about this point? Slope's negative. This point, slope's negative, slope's negative. What's it doing as we get towards 0? So they start off pretty much 0, and then they get negative. What's happening there as we get to the origin? What are the slopes doing as we do this? They're getting larger and more negative, right? So is that a hole on the graph of the derivative or an asymptote on the graph of the derivative? Yeah, it's an asymptote because the tangent lines are getting more negative, but they're also becoming vertical. So we have to start pretty much at 0, but then we know they're negative, right? All of these slopes are negative, and they get more and more negative. So we just have this graph kind of diving off to negative infinity. How about this piece right here? What are the slopes doing? They're really positive right here, aren't they? What's the slope right here? It's pretty much vertical. So again, that doesn't tell us where we start on that segment on the graph of the derivative. The ones kind of next to it as we move to the right do. This slope is really positive. It's a little less positive. It's a little less positive. So they start out super positive and approach 0. We start off super positive and they have to approach this 0. And then after that horizontal tangent at at +2, what are our tangent lines doing here?
More negative.
More and more negative. They start out pretty much flat, then they're negative and more negative. So they start out pretty much flat and get more negative. So that looks like, I don't know, they're kind of stopping there at an x value of 4, so we'll do the same. There's the derivative. Anyone have any questions on that? So the theorem here that we're looking at takes a notion from 2.6 and then ties it into this idea of being able to find a derivative somewhere. So we're relating differentiability and continuity by this theorem in the sense that if you have a derivative that exists somewhere, the function has to be continuous there. So differentiability means continuity or implies continuity. Just like if the street's wet outside, or just like if it's raining rather, it would imply that the road is wet. Okay. So the if-then statements are meant to be read that way, just that way only. It's like a one-way street. Differentiability, then it's continuous. We can't say that if it's continuous, then it's also differentiable. So it doesn't work that way. There's, like for theorems in math, there's always this sort of logic that follows it. So like you can have a statement, there's things called the converse of the statement, where you flip the statement around. And then the contrapositive of the statement, where not only do you flip the statement around, but then you negate both of the arguments. So like if today is Thanksgiving and it's Thursday, that's a true statement. But if I flip the arguments around and said if today is Thursday, then it's Thanksgiving, then I no longer have a true statement, right? Today is Thursday, it's not Thanksgiving. So that flipping of the statement around doesn't always yield an equivalent statement. What does always yield an equivalent statement, if you are talking about a true statement, like if today is Thanksgiving, then it's Thursday, is flipping it around and then negating it. So if today is not Thursday, then it's not Thanksgiving. That's also true. So the contrapositive of a true statement is always true. That's not the case for the converse, where you just reverse the order of the if-then. So the reason, the reason we mentioned that is because there's this alternative version of Theorem 3.1, where 3.1 says, if it's differentiable, then it's continuous. Well, we flip that around and then negate it and say, if it's not continuous, then it's not differentiable. So that's how we get the alternative version. It's simply the converse of Theorem 3.1. So the alternative version, just the converse of Theorem 3.1. I'm going to expect you to remember the logical stuff, but I think if you go on in math, it's really helpful, especially when you have an if and then statement. To flip it around and negate it, you can get an equivalent statement. So that's kind of what we work with exercises, because looking at a graph, you can almost immediately tell where most graphs are not continuous, right? So if we have this graph right here and say, is this function continuous at A? Clearly not. Since it's not continuous there, we cannot define a derivative there. Not continuous means it's not differentiable. The derivative doesn't exist. So more so in practice, the alternative version of that theorem is utilized. Okay. So you got to remember, differentiability implies continuity. Continuity does not imply differentiability. Right? So the easiest way to remember that continuity doesn't imply differentiability is just to think of the absolute value function. So if you're thinking about differentiability and continuity in your head, and you say, well, I forgot which one implies the other, then just think of the absolute value function. Can I define a derivative at this point? No, because it's a sharp corner. You got to remember that too. But once you remember that, and you say, well, I can't define a derivative there, but is the absolute value function continuous there? Yeah. So it's not differentiable, but it is continuous. So just because it is continuous doesn't mean it's differentiable. Continuity doesn't imply differentiability. Here's an example of that. The function is continuous at 0, but it's not differentiable at 0. So the converse of Theorem 3.1 is not true. That is, continuity if f of x or whatever is continuous, then f of x, continuous at a point, continuous at a, then f of x is differentiable at a. That statement is false. And again, we've got our absolute value as the perfect counterexample to why that's false. Okay. Do you all have any questions on either one of these theorems? They're kind of the same thing, but. So we're going to look at this graph again and ask the questions. 1, where is the function not continuous? And 2, where is the function not differentiable? So part A will say g of x is not continuous at what x values? -2 and +2. Do you all agree with that? Okay. Part B, g of x is not differentiable at what x values? -2 and +2, yeah?
Zero.
Zero success, vertical velocity.
Yeah. But notice those two are freebies from that theorem. The theorem says if your function's not continuous, then it's not differentiable. So we automatically know these two are true because of theorem 3.1. So theorem 3.1 guarantees that it's not differentiable where it's not continuous. Okay, and the other location was at x equals to 0, right? Why is the function not differentiable at x equals to 0?
Because G prime has a vertical velocity.
Right, because there's a vertical tangent. We saw that when we graphed this, right? The tangent line gets more and more vertical right here. So this is a vertical tangent. Okay. So there's 3 values that function's not differentiable, but only 2 values where it's not continuous. So a theorem like that is like a really good candidate for like a true false or a short answer type question. So I don't expect you to know it verbatim, like have everything memorized, but just know what it says. Differentiability means continuity, and not continuous means not differentiable. It's the same statement. Yeah.
Does f of x need to be defined for it to be continuous?
Yeah. So the function has to be defined to be continuous at that point.
Doesn't 0 go to negative infinity though?
On the graph of G,
Yeah.
no. So we can like that really basic notion of continuity. Can we draw this graph without picking up our pencil? Is sufficient here. So if we could exaggerate that graph, it would just look like this.
But it's defined somewhere at 0.
Yeah. Right. So like you've got an actual point here. If you didn't have a point there, that would have to be clearly indicated to whoever's looking at that graph. That you would have to have something like that to clearly illustrate that it's not defined at 0.
And even though it approaches 0 on the actual graph, it still approaches negative infinity on the derivative.
Correct. So like what are our tangent lines approaching from this direction? Well, those slopes are really negative, right? So as we approach 0 from the left, that our tangent lines we would say is negative infinity. But as we approach 0 from the right, our tangent lines are positive, getting more positive. So as we approach from the right, we have our tangent lines are approaching positive infinity. That's a little more technical than really what we get into, but that's exactly what's happening. So no, yeah, that function is defined at 0. Otherwise, we would see some clear indication. Any other questions? I think that's the end of 3-2 then. We'll go ahead and take a break, but what we're looking at from 3.3 and on are shortcut rules to take a derivative. So these rules are going to give us a means to not have to compute the limit as h approaches 0 every time we want to find the derivative of a function. So 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, and 3.9, and 3.10, those 8 sections give us new derivative rules or derivative techniques. These derivative rules in every section, they pile up really quickly. So I strongly recommend that for each of these derivative rules that you make a flashcard. That way you can just test over them. Because once we get to like 3.7, then it's like, hey, here's a function that involves 3 different derivative rules in order for me to take it. And if you don't know your derivative rules, you're going to be pretty stuck. So since they do come in so quickly, I recommend that you do something with them so that you're looking at them every day. How many are we learning? Well, there's like a couple of techniques. The product rule, there's a quotient rule, there's a chain rule, there's implicit differentiation. There's derivative of trig functions, derivative of inverse trig functions, derivative of exponentials, logarithms. So like with all of that, like you could have a function that has all of those things, and it could say find the derivative of the sine of e to the square root of x all over x to the 4th times cosine cubed. So then you've got like multiple derivative rules you have to remember. How do I take the derivative of that? So it gets pretty tricky pretty quickly, just because there's so many things to have to remember. Yeah, so as we go through these, write them down somewhere and look at them, 5 minutes a day is probably all you would need to do. Any other questions before we go on break? All right, so the first derivative rule that we get is the derivative of any constant is 0. So hopefully that just makes intuitive sense. What's the slope on a horizontal line? The slope is always 0. So like if we were taking, or we were asked to find the derivative of 5, 0, derivative of pi is 0, and so forth. The derivative of e to the pi, 0. Those are all constants with respect to x. They're all if we graph 5, if we graph y equals pi, if we graph y equals e to the pi, they're all horizontal lines. Okay. The next rule is the power rule. Your textbook will keep refining what n has to be. So here when it's first presented, they say n is a non-negative integer. It just means it's a positive whole number. But ultimately, once we get more tools and theorems, they'll refine that in a more technical way. But eventually, we're going to get to the point where n is any real number. So we might as well just state that right now. So the derivative of x to any power, you see the original power n comes out front to multiply, and then we take 1 away from the power. So the derivative of x to the 4th would simply be 4 times x to the 3rd. So the original power comes out front, multiplies x to the 1 less power. The power rule also applies to radicals, right? Because if I have like the cube root of x squared, we know that's the same thing as x to the 2/3. So we'll write one of those here. If we have to take the derivative of the cube root of x squared, the way we do that is we just think of it as a power. That's the derivative of x to the 2/3 power. And then the power rule says that we're going to pull the original power out front to multiply x to the 1 less power. So we have 2/3 minus 1/3. So the derivative of x to the 2/3 is 2/3 x to the 1/3. So that, you probably can then immediately see the utility of something like this.
So for that one, I feel like I missed something. So like, are you subtracting like 1 from n? So like 2/3 minus 1?
Yeah, so you subtract 1 from the original power that was present on x. The original power present on x was 2/3. So we're subtracting, we're subtracting 3/3, which makes this negative 1/3. That's probably why that was confusing. Yeah, thank you. Yeah.
Just to clarify, so each time we take the derivative, we basically subtract 1 from like the power.
Yes.
Okay, cool.
Yeah. Well, the original power comes out front to multiply, though. Yeah, does that make sense? Does anyone have any other questions about that? So, you know, like like with x to the fourth, like if we had to find the derivative of x to the fourth from section 3.2, we would have to compute the limit as h approaches 0 on x plus h to the fourth minus x to the fourth all over h. So it's really tedious to multiply x to x plus h 4 times, collect like terms, simplify, right? If this were x to the 100th, you know, it's even more tedious to do the derivative by hand, by definition. But by this theorem here, taking the derivative of x to any power is now very simple. The derivative of x to the 100th power is just 100 times x to the 99. So I don't have to go through this whole limit procedure anymore. So every derivative on the exam will be taken with a derivative rule. With the exception, there will be one question that says, here's a function, use the definition of the derivative to compute that. So I say that, and I'll remind you as we get closer to the exam, because on a lot of problems like find the derivative of x to the 100th or find the derivative of sine, people are still wanting to compute the limit as h goes to 0, and that's just really tedious. The only time we're going to revisit this limit definition is for one question on the exam and in your homework, of course. Every other derivative we do, we're going to use all of these shortcuts. Constant multiple rule, it just says if we've got a constant times a function of x, then the constant can get pulled out of the derivative and multiplied in afterwards. So like the derivative of 3x to the fourth, that theorem says that's the same thing as taking 3 times the derivative of x to the fourth. So with this notation, like we said, this means take the derivative with respect to the variable x. You've got 2 things being multiplied. One of those things doesn't have an x present. So the derivative doesn't affect the 3 multiplying the x to the fourth. The derivative operation only affects the x to the fourth itself. So again, we see that here in this step. So the derivative of x to the fourth again, we have 4 times x cubed, or 12x cubed. Still the same kind of thing as the power rule, right? The 4 comes out front to multiply this 3, and then we take 1 from the power to get 12x to the third. Questions on that? So don't get this mixed up with the first property that said the derivative of a constant is 0. That's just when the constant's alone. If the constant's attached to x with multiplication or division, then it just comes out of the derivative to multiply or divide after. So this works with things like if we had to find the derivative of I don't know, let's say x squared over 2. We've got a constant of 1/2 multiplying x squared. So we could say if we wanted to, well, that's just x squared, sorry, 1/2 rather, times the derivative of x squared. The derivative of x squared is 2 times x to the first. So we have 2 times the half x to the first. Does that make sense? Are there any questions? So, again, it's almost like a compensation. We don't have to compute things long way anymore, but now there's like 10 different derivative rules we've got to remember. So it's a trade-off. The sum rule also works with the difference. Let's go ahead and write that in. If you're taking the derivative of a function plus or minus another function, then it's simply the derivative of the first thing plus the derivative of the second thing plus the derivative of the third thing, and so on and so on. In other words, what this rule is telling us is that that derivative operator is, we can distribute the derivative operator across sums and differences. So it's So that's what we're doing. The derivative goes here, plus or minus the derivative here. For example, if we had to take the derivative of 2x cubed minus x squared, we see there's two functions of x separated by subtraction. So we're going to take the derivative of 2x cubed and then subtract off the derivative of x squared. What's the derivative of 2x cubed?
6x squared.
6x squared, do y'all agree? 6x squared. The 3 comes out front to multiply the 2. 3 times 2 gives us 6, and then we take 1 away from the power, x to the second. So minus derivative of x squared is 2x. So that's the derivative of 2x cubed minus x squared. And once you've done a few of these, you're probably not going to write it out as we're writing these things out now. You're just going to do the derivative, right? So like once you've practiced them, I don't know that you have to write it out completely. Like by exam time, if it said take the derivative of 2x cubed plus 3x squared plus x plus 1, that you would just say, all right, well, what's the derivative of 2x cubed? What's plus the derivative of 3x squared? Plus the derivative of x. What would the derivative of x be? 1, right? Because it's the 1 is the power on x, comes out front, and then we take 1 away from the power. So it's really x to the 0 is the derivative, and x to the 0 is 1. Plus the derivative of 1, what's the derivative of 1? 0. So, I mean, that's pretty much what you'll be doing, just to take a derivative like that. You don't have to write all of these properties out and apply them individually.
Would we have to simplify that one? Or can we just leave it like that?
Yeah, so that's one of the biggest things with finding derivatives is once we get to chapter 4, and even sometimes in chapter 3, we do things with the derivative. So, on those graphs where we had like something like this, what if we wanted to know where what is the x value of this point? We have to first say, all right, well, what is the derivative? And we know at that point the derivative, the slope of the tangent line, is 0. In other words, the derivative at that x value there is 0. So sometimes you do have to take the derivative function, set it equal to 0, and solve for x to find where that's at. So simplifying derivatives is not something that I really want to focus on for the third exam, because I just really want to focus on the mechanics behind finding the derivatives. So on the exam, it'll say find the derivative and simplify, or it'll just say find the derivative. If the instructions say simplify, then you would want to simplify it. This thing, the only thing we could do with 6x squared minus 2x is factor out a 2x. So At this point, we're just going to leave our derivatives as they are. If we encounter a situation where we do have to simplify them, then we will. Any other questions about any of this so far? And then the final derivative rule for now is the derivative of e to the x is itself is e to the x. There's really no other examples we can show there. We could apply like constant multiple rules and stuff like that. So if we had like the derivative of 5 times e to the x, for instance, what would the derivative of 5 times e to the x be? 5 e to the x, right? The constant comes out, multiplies the derivative of e to the x. All right. Okay, so just with a few rules, it really like opens up the doors to what kind of functions we can take the derivative of now, without having to compute that long-winded definition, limit as h goes to 0, etc. So let's look at example. Write the equation of the tangent line for the function 2x minus 1/2 e to the x at the point 0, negative 1/2. And then find the points on the graph where the tangent line is horizontal. So we'll see that quite frequently. Where the tangent line is horizontal, we've already talked about it, but anytime you're asked to find where the tangent line is horizontal, you have to take the derivative function, set it equal to 0, and solve for x. That's always the procedure to find a horizontal tangent. So one of the main benefits of that is maybe you remember graphing polynomials in algebra and trig or pre-calculus. And so like the polynomials you graphed, look something like that. But the best you could ever do is say, all right, well, here's an x-intercept, here's an x-intercept, here's an x-intercept, here's an x-intercept. I know the in behavior because of the leading term. And then I know what's happening at each 0 because of the multiplicity, right? The multiplicity is odd, we pass through the 0, the multiplicity is even, it bounces off. And so you were left wondering, well, how do I know how far to go up before I turn down? How far do I go down before I turn back up, etc.? These points right here you couldn't find because it takes calculus to find out where those points are. And the way we find those points is say, all right, well, on this, whatever this function is, where does this function have horizontal tangent lines? And that gives us the minimums and maximums. So it is a highly useful thing to be able to find where the tangent line is horizontal. Okay, so the first part though is to write the equation of the tangent line at the point 0, negative 1/2. Equation of the tangent line, remember, is y minus the y coordinate equals to the slope of the tangent line times x minus the x coordinate. So really, when you're asked to find the equation of the tangent line, you just need to find the slope of the tangent line at that point. Okay, so it's worth pointing out, because people will do this. This slope of the tangent line that we're talking about right there in the equation of that line, that's always a number. You never put your derivative function in for the slope of the tangent line. Remember, the derivative function is the slope of the tangent line at any x value. When we say the equation of the tangent line, at this point, we want a specific slope, or the derivative evaluated at a particular x value. So that will always be a number when you write the equation of a tangent line. You never will put your derivative function there. So the first thing to do is to find the derivative function. So we find f prime. Given that our function's 2x minus 1/2 e to the x, what is the derivative of 2x minus 1/2 e to the x? So we have the difference of two functions of x. What's the derivative of 2x? Is it 2? Remember, that's x to the first. So when we say the derivative of x to the first is 1 times x to the 0th power, which is 1, right? But it's multiplied by 2. 2 times 1 is 2. Derivative of negative 1/2 e to the x. Yeah, just like the derivative of 5 e to the x was 5 e to the x, the derivative of negative 1/2 e to the x, excuse me, is negative 1/2 e to the x. So there's the derivative of f. And specifically, we're asked to write the equation of the tangent line at the point when x is 0. So now we've got to take our derivative and evaluate it at 0 to get the slope of the tangent line. So remember, this here, this is the slope of the tangent line at all x values. But we want the slope of the tangent line specifically at that one point. The slope of the tangent line at the point 0, negative 1/2 is f prime of 0. We're plugging in a 0 to our derivative, which is 2 minus 1/2 e to the 0. And what does that give us? 1.5. 2 minus 1/2. So we did quite a significant amount of work in just a few steps. Are there any questions? Yeah.
Can you walk me through the last step of that?
This one here?
Yeah,
So e to, like this part,
yeah.
e to the 0, anything to the 0, well, any number but 0 to the 0th power is 1. So that turns into 2 minus 1/2 times 1, or 2 minus 1/2, which is, what is that? 8. Sorry, 4 over 2 minus 1 over 2. So that's 3 over 2.
Yeah, I just need that like spell
Okay.
out.
Okay, yeah.
Thank you.
You're welcome. So the issue is finding the slope of the tangent line at a point. You've got to find the derivative and then plug in that x value to your derivative. And that's going to give you the slope of the tangent line at that point. So 3/2 is what we're putting in for this up here. Not the derivative function itself, but the derivative at the point. Is everyone clear on that? All right, we'll see when the test rolls around. There's many people that still just want to put f prime of x right there. Never do that. It's always a number there. All right, any other questions on this? Yeah.
would you say it's more efficient to do it like this, where you find the f prime and then plug in, rather than doing like how we did before, where we plugged it into the definition and then kind of worked it through?
Oh, yeah, yeah, much faster. Yeah. So like that problem would be then, you know, if remember the definition of the derivative at a point, the limit as h approaches 0 of f of a plus h minus f of a all over h. Yeah, it's going to be really hard to do that with our exponential e to the x. So yeah, you'd have to compute f of h minus f of 0. We already know what that is. It's given to us as that point. But then f of h is 2h minus 1/2 e to the h. So how do you compute this limit and simplify this? It's very difficult. Any other questions? Equation of the tangent line on that function. So we have, just solving this for y. Y equals to 3/2 x minus 1/2. It's the equation of the tangent line. So there's our function. We will found the equation of the tangent line at that point. It's 3/2 times x minus 1/2. Maybe this is better. Everybody okay with all that? Okay. Where, what x values or values does f of x have a horizontal tangent? So like we said above, to find where we have horizontal tangents, we have to take our derivative, set it equal to 0, and solve for x. Our derivative was 2 minus 1/2 e to the x. So we've got to figure out where does 2 minus 1/2 e to the x equal to 0. So that's when 2 equals 1/2 e to the x. Just add that to the other side. Multiply by 2, clear the fraction. When does e to the x equal to 4? How do you solve for exponential base e. Take the logarithm base,
The natural log.
base e, right? Natural log undoes e. Ln of e to any power is just the power, and the ln of 4 is the ln of 4. Whatever that is, x value of ln 4 is, I don't know, 1.386. So on that graph then here, we could find this particular point. You see that the graph of f of x, the 2x minus 1/2 e to the x, does have a horizontal tangent right there. X value ln 4, right? 1.386. Any questions on that? Can you scroll up just a little bit? Sure. So equations of tangent lines, you have to find the derivative and then plug the x value in. That's your slope. Where your tangent line is horizontal, you have to set your derivative equal to 0 and solve that equation. Yeah.
Will we ever be graphing them with graphing calculators and maximum and minimums with the 0 values, or just visually?
Yeah, there is a section in chapter 4 where we graph stuff. So yeah. We'll have to use, in chapter 4, we'll have to use this as part of our graphing technique because this finds those minimums and those maximums for us. So yeah, we eventually come back to using this to graph.
Are we gonna take like the derivative of the derivative more and more?
Yeah, we're gonna look at that.
Okay.
Yeah, I think that's coming up shortly.
Okay.
Yeah. Okay, any other questions? Yeah, you can take the derivative of the derivative. You can take the derivative of the derivative of the derivative.
Didn't they have a name for like each one of them? Compositions? No, it's like, I forgot. It has like funny names, right?
First derivative, second derivative, third derivative, fourth derivative.
Yeah.
Yeah.
They have a name, right? Each one.
It depends on like what function you're dealing with. Like if you talk about if you're talking about like measuring your position, you know, it's worthwhile to look at because we have the knowledge of what a derivative measures, right? So like if this were your position function, and we're measuring miles per hour, close.
It's not
Like,
so that- no, when we take the derivative.
Yeah, you take the derivative. Like if I told you to find the derivative at this point, you would say it's just that slope, right? But what are the units here? If I say this, whatever, let's say the slope is 10, what are the units?
Change in miles?
Huh?
Change in miles over hour, or velocity?
Yeah, right. Because remember when we compute a derivative, it's a small change in y over a small change in x. A small change in miles over a small change in hours. So if I compute a derivative, my units are always the y units over the x units. If I'm looking at a position function and I find a derivative, I now get a velocity. we can tell that just from the units, right? We divide miles and hours, we get miles per hour. That's a speed or a velocity, not a position anymore. So there are actual interpretations of higher order derivatives. If you take the derivative of position, you get velocity. If you then take the derivative of velocity, you get acceleration. If you take the derivative of that again, you get something else. It's called jerk. If you take the derivative of jerk, you get snap, right? So like there are physical interpretations of higher order derivatives. And yeah, it is snap, crackle, and pop. They did name that. If anybody's old enough to remember those cereal people. But so yeah, we do look at higher order derivatives, and they do have physical interpretations. I guess we're done with that. Okay. So we'll look at a couple more functions and just find the derivative of these functions. So what's the derivative of e to the third power? 0, I heard 0. What do y'all think? E to the third, there is no x there. E to the third is a constant. Derivative of a constant is 0. Okay, the square root of x over 3. So remember our rules, we've got a power rule and a constant multiple rule. So you want to think of it in that sense. I don't want to think of the square root as the square root. I want to think of the square root as x to the 1/2 over 3, or 1/3 times x to the 1/2 is what that function is. Before I even take the derivative of that, is 1/3 x to the 1/2 is how I'm thinking of it, just so I can apply those rules to it. So f prime then, the 1/3 is not affected by the derivative, so it's still hanging out 1/3 times, what's the derivative of x to the 1/2? 1/2, the power comes out, multiplies x, subtract 1 from the original power, 1/2 x to the negative 1/2. So we actually then have 1/6 x to the negative 1/2. Is everybody okay with that? Even now, we're not writing out all of the individual derivative rules. Anyone have any questions? You might also see these with positive exponents. I don't really have a preference. If you want to leave it as with negative exponents, that's fine. If you want to write it like this, it's also fine. Doesn't really matter. So how about number 3? Do we have a rule for the product of two functions of x? We've got the square root of x as one thing times x minus 1 is the other thing. So that's the problem at this point, right? At this moment we don't have a rule that says how do we take the derivative of one function of x times another function of x. That's the next section. So here's f of x, here's g of x. So once we do get the product rule, it's still going to be easier to do it the way that we're about to do this, because we can actually simplify the function first before we take the derivative, right? That's always a good practice. If someone says take the derivative of this function, and you can simplify the function, then simplify it first. Because you're dealing with something simpler, the derivative should be something simpler to compute. So we're just going to simplify this first. So we're going to just say that's x to the 1/2 times the quantity x minus 1, and then just distribute that in. So we have x to the 1/2 plus 1, x to the 3/2 minus x to the 1/2. So then we see we just have now no longer a product of two functions of x, but two functions of x that are added or subtracted together. And they're both powers. So what is the derivative? What's f prime equal to?
Two x times to the second power.
3 over 2 x to the
To the 1/2, right?
1/2.
Yeah. It's minus one.
What do y'all think? Is that the
Yeah.
derivative of x to the 3/2? 3 over 2 comes out, multiplies. X to the 1 less power. So we have x to the 1 less power. Right? X to the 1/2, okay. Minus the derivative of x to the 1/2. Well, I guess we already did that above. 1/2 x to the negative 1/2. So that's pretty much it. We'll call it good with that. Questions on example 3? I would recommend starting these homeworks as soon as we cover the material, because it's a lot. There's 11 sections in chapter 3. All right, example 4. What are we going to do for the derivative in example 4?
Simplify.
Let's simplify that as well. How does that simplify? F of x is equal to yeah. Once you simplify it, it becomes a pretty easy function. It's x squared minus 1. What's the derivative of x squared minus 1?
2.
Or 2.
Or 2 to x.
2 times x? What do y'all think? 2x, the derivative of x squared minus 1? Derivative of x squared is 2x. The derivative of negative 1 is 0. I'll write that here. Just if you're thinking of it this way.
Plus.
So that's much simpler to do. Even when we look at how do we take the derivative of a quotient, something like this that you can simplify, is going to be, probably 5 times or more easier to do if you simplify it first. Yeah.
When we're computing like these derivatives, do you expect us to do like the same thing that we did with the limits, like write the limit like for each like part of it, or like is it okay if we like just like simplify it down like until the end before we write like f prime of x equals like whatever derivative it is?
Yeah, so you can simplify it and then take the derivative. Just like with the limits, you can simplify the expression in the limit first, as far as you can get it, but then that simplified expression the limit needs to be in front of that after. Same thing here. Simplify the function as far as you can, and then put that in front of the derivative. Honestly, some of these things, by the time we've done enough derivatives, a lot of this stuff, if these are exam questions, there's virtually no work to show. It's you virtually just go from where we started to where we finished. There's like 1 or 2 steps at the most. But for more complicated ones, yeah, there are additional steps that we should write out to keep track of everything. Okay. Again, similar thing with example 5. It's a little less obvious now because we don't know the quotient rule. But again, even if you know the quotient rule, it's going to be a lot more efficient to simplify first if you can. So simplify, especially if you're stuck, if you're trying to take the derivative of a product or a quotient like these last 3 examples, if you're totally stuck on that, then you should try to simplify it. And that'll be the same idea applying that we're applying here will also apply once we start looking at integrals in chapter 5 as well. So we're going to simplify this as x plus 1, x minus 1. That's a 1. All over x minus 1. Okay, so that's f of x. We're going to take the derivative of x plus 1. What's the derivative of x plus 1? 1? Do you all agree? Derivative of x is 1, plus the derivative of 1 is 0. So that's the slope at all points on x squared minus 1 over x minus 1. Where is our derivative defined? All of x certainly appears that way because the function is constant. F prime is constant. You can plug in any real number into a constant. Except 1, right? It doesn't make sense to say the derivative of this function is always 1 because this function right here doesn't exist at x equal to 1. So the derivative is valid. Remember, the derivative is connected to the original function. It's just derived from the original function. Original function's not defined at 1. The derivative is not defined at 1. All x such that x is not 1. Here, let's see that way. Does that make sense? If your function's not defined somewhere, you cannot define a derivative at that location. Same thing with the example 4 above. That derivative, although it was linear 2x, that derivative is not defined everywhere on that function. The derivative is 2x when x is not 0. Because of this right here. It's supposed to be whatever. The function's not defined there, you can't define a derivative there. Any questions on those? So we do have the next topic is the higher order derivatives. We can come back to that. We're already behind, so we're going to skip to higher order derivatives. The second derivative is defined here. The second derivative. So if you'll notice, the second derivative is defined as the derivative of the first derivative. And then in general, the nth derivative is just the derivative. The nth derivative is rather the derivative of the n minus 1th derivative. So like, that means find the 6th derivative, but the 6th derivative is the derivative of the 5th derivative.
Isn't there a point where you can't take any more derivatives?
Some
Depending on
functions, yeah, depending on the function. Like if we took the derivative of x squared and got 2x, and we take the derivative of 2x and get 2, then we take the derivative of 2 and get 0. Like you're done. Any other derivatives after that will always be 0. But if we take the derivative of e to the x, it's e to the x. The second derivative is e to the x. The third derivative, the millionth derivative is still e to the x. So some functions don't really zero out with higher order derivatives. It just kind of depends. So yeah, the 6th derivative is the derivative of the 5th derivative. Makes sense. really, for us, primarily, we're only concerned with the first and the second derivatives. So that, like, physically, the first derivative would tell us velocity, and the second derivative tells us acceleration. For graphing, the first derivative tells us where we have like those minimums and maximums, and the second derivative tells us sort of the shape of the graph. Is it like this, or is it like this? All right, so let's look at a specific example. Find find the third derivative. Given f of x is the square root of x. You just have to go in order. You've got to find the first derivative and the second before you find the third. So the derivative f prime of the square root of x is what now?
1/2x to the negative 1/2.
Yeah. That's a really common one. We've seen this 3 times already. 1/2 x to the negative 1/2. Remember, we're thinking of anything that involves roots as their respective powers. So then the second derivative, f double prime, is just the derivative of the first derivative. So again, you don't necessarily have to write all of this out. But we do need to take the derivative of 1/2 x to the negative 1/2. So what is the derivative of 1/2 x to the negative 1/2?
X to the negative 3/2.
Negative 1/4 x to the negative 3/2. What do y'all think? So this 1/2 out front, sorry, the negative 1/2 as the power comes out front to multiply this 1/2, so that gives us our negative 1/4. And then we're subtracting 1 from that original power, so we have x to the negative 1/2 minus 1. So we have minus 3/2 for the new power. And then the third derivative. So, sometimes people will write triple prime like this, but usually things above triple prime, they'll just write the number in parentheses up here. The third derivative is the derivative of the second derivative. So we've got to take the derivative of negative 1/4 x to the negative 3/2. Power rule again, negative 1/3, or sorry, negative 3/2 rather, times the negative 1/4 gives us a positive 3/8 x to the
Negative 5/2.
negative 5/2. Negative 3/2 minus 2/2 again. So then the next iteration, you'd have something x to the negative 7/2. The next derivative, something times x to the negative 9/2, and so forth and so forth and so forth. There's our third derivative. Does anyone have any questions? All right. I know we skipped a few examples because we are behind, but as always, if you encounter something in the homework that you would want to look at, I'm happy to look at those before class or as class starts. All right. I think that's going to be the end of 3.3 then. Yeah, end of 3.3. we'll start 3.5 today. We're supposed to, I think we were supposed to get to starting 3.5 today if we're gonna stay on schedule. Yeah, so we're a little behind. 3.4 deals with the quotient rule and the product rule. So how do we take the derivative of f times g? We're going to use this example where we have to take the derivative of, a product of something we know what it should turn out to be. So if we take the derivative, let's say, of x cubed times x to the fourth, what should the derivative of x cubed times x to the fourth be?
7x to the 6.
Yeah. So before we take the derivative, again, I don't know how to take the derivative of a product at this point. I'm just going to simplify this function first and then take its derivative. So we've got x to the 7th. Power rule is 7x to the 6th. So even though I don't know how to take the derivative of x cubed times x to the 4th at this point, we know it should be 7x to the 6th. So the following step is just going to show for this particular example, or any other for that matter, if I were to say that the derivative of this product is equal to the derivative of x cubed times the derivative of x to the 4th, that should always be the case if that is actually the product rule, right? And we'll just test that out. We take the derivative of x cubed and multiply it by the derivative of x to the 4th. Do we get x to the 7th, or 7x to the 6th rather? No, clearly not. We've got a 3 times 4. We've got x to the 5th. So this should show us that it's not as straightforward. We can't take the derivative of a product by just taking the product of the derivatives. Like the derivative sort of distributed across sums and differences, the derivative does not distribute across a product. It's not, unfortunately, not that straightforward. So we'll put an asterisk there. And, just at least in this case, it leads us to say that the derivative of a product is not the product of the derivatives. That is, the derivative of f of x times g of x is not what we just did. It's not the derivative of f times the derivative of g. If it was, we wouldn't have the product rule, because it would just be, I'll just take the derivatives and multiply them together. So the product rule is in Theorem 3.7. To take the derivative of the product, we have f prime times g plus g primes times f. And usually, I don't know, there's a couple of ways to remember these quickly, I guess, or mnemonically. So you have like a factor 1 and factor 2 times each other. So we have this first times the second. So we say the derivative of that product is the first times the derivative of the second plus the second times the derivative of the first. these two things are one thing. They're multiplied. These two things are another term.
What if we put like h of x in there? How would that affect that?
Yeah. All right. So what if there's three things multiplying? How would that affect it? So some way or the other, you've got to remember to yourself, if you see a product, I've got to do the first thing times the derivative of the second, plus the second thing times the derivative of the first. However you want to remember that, totally up to you. But if we have the derivative of f of x times g of x times h of x, you have to think of a first and a second. It doesn't matter which ones you call first and second, but you do have to think of just a first and a second term. So perhaps when we take the derivative of this, we would say that's the first, and this is the second. The thing is when you take the derivative of the second, you then got another product rule you have to use. So this is still, the derivative of three things is still the first times the derivative of the second. Plus the second times the derivative of the first. But here you have another product rule. So from that you would also get two terms, right? First derivative of the second, second derivative of the first. So that you can see even when multiplying three different functions of x, like maybe a logarithm, an exponential, and a trig function, it's pretty convoluted to take the derivative of three things multiplied by each other. But you just iterate it with the product rule here. If we had five things, you could call the first thing the first and the next four factors the second. You could call the first three products the first and the last two the second. It doesn't really matter how you group the products together. You just need something times something else, and then you would subsequently keep breaking that down. We don't really see too many of those at all, if any, but they're there. Anyone have any questions on that before we go? So start doing your homework, start making note cards. This stuff comes fast. See y'all.